Good morning, students. Our today's topic is quotient space. We will prove that the quotient space is a normed space, and if a space is Banach space, then its quotient space is also Banach space. So the theorem is, let M be a closed subspace of a normed space X. Then the quotient space is a norm space with norm given by x plus m norm, which is defined by the infimum of the collection of the norms of the elements of the form x plus m, where this m belongs to the closed subspace M. We will prove that this function defined by this formula defines a norm on this quotient space x by m. So in order to prove this, we are to prove the four properties of norm. First property, we will prove norm is non-negative. So let us take an element x plus m belonging to the quotient space x by m. Now, because for every element m belonging to m, norm of x plus m is non-negative, it means this set consisting of the norms of this kind of elements x plus m, that is a set of non-negative real numbers, and therefore its infimum that will also be non-negative. So we have proved the first condition, that norm of x plus m is non-negative for every element x plus m belonging to the quotient space x by m. Now next property. In the next property, we are to prove that norm of x plus m is 0 if and only if the element x plus m is 0. Here 0 means the 0 of the quotient space x by m. So let us prove the first part of this. Let us take firstly an element x plus m belonging to the quotient space x by m such that the norm of this element is 0. By definition, norm of x plus m means the infimum of the set of norms of the elements x plus m where this m belongs to set m. Now because norm is 0, it means the infimum of this set is 0. Now by definition, it means there exists a sequence mk in the closed subspace M such that the norm of x plus mk approaches to 0 as k approaches to infinity. Now because this norm approaches to 0, it means x plus mk approaches to 0 as k approaches to infinity. Or we can say that mk approaches to minus x as k approaches to minus infinity. Now because this is a sequence in M and M is closed, so this element minus x will again belong to M. Because the set is closed, if and only if there exists a sequence which converges to x and that x belongs to the same set M. So we can say that minus x belongs to M. So we have proved that x plus m is equal to m. So we have proved if the norm of element is 0, then the element itself is 0. Here 0 means the 0 of the quotient space x by m. The 0 of this quotient space, that is m here. Now we'll prove the converse. Conversely, let us take the element x plus m belonging to this quotient space is 0. 0 means m. So we have taken x plus m is equal to m, and we are to prove that the norm of this element is 0. Now because x plus m is equal to m, so this means x belongs to m. Now let us find the norm of x plus m. Now by definition, norm of x plus m means the infimum of the set consisting of the norms of the elements x plus m where m belongs to m. Now we can take x plus m as y. So this will become infimum of the set of norms of y where y belongs to m. Now because M is a closed subspace of X, and therefore M is a vector space, and every vector space has additive identity. 0 is the additive identity of X, and therefore we can say that the infimum of this set, that will be 0. So we have proved if the element is 0, then the norm of that element is also 0. So we have proved the second condition of norm. Now third property, absolute homogeneous property. In this property, let us take an element x plus m belonging to the quotient space x by m, and let us take a scalar alpha. Now let us find norm of alpha into x plus m. Now by definition of scalar multiplication in a quotient space, alpha into x plus m can be written as alpha x plus m. Now its norm is given by the definition infimum of the set consisting of norms of the elements alpha x plus m, where this element m belongs to the closed subspace M. We can take alpha common from this expression. Inside we have x plus m by alpha. Now we can take m by alpha as m dash, that is also an element of M. So we can write alpha into x plus m norm is equal to the infimum of the set consisting of the elements alpha mod into norm of x plus m dash. Now this m dash belongs to M. We can take it outside. So inside we have infimum of the collection consisting of the elements x plus m dash norm, where m dash belongs to M. By definition, this is the norm of x plus m. So we have proved absolute homogeneous property. Now the last property, that is the triangle inequality. So let us take two elements x plus m and y plus m belonging to the quotient space x by m. We are to prove that x plus m plus y plus m norm is less than or equal to x plus m norm plus y plus m norm. So let us start from left side. Let us take the norm of the sum of elements x plus m and y plus m. Now by definition of addition in a quotient space, this expression can be written as x plus y plus m norm. Now by definition of norm, this is the infimum of the set consisting of the norms of the elements x plus y plus m, where m belongs to M. Now we can apply the definition of infimum. So by definition of infimum, for epsilon greater than 0, we can take an element say m1 belonging to M such that the element is less than or equal to infimum plus epsilon. Now here the element is x plus m1 norm, that is less than or equal to the infimum is x plus m norm. So x plus m1 norm is less than or equal to x plus m norm plus epsilon. Similarly, again applying the definition of infimum, there exists an element m2 belonging to M such that this element is less than or equal to infimum plus epsilon. So element is y plus m2 norm. This is less than or equal to infimum is y plus m norm plus epsilon. Now let us apply the triangle inequality for these two elements x plus m1 and x plus m2. So according to triangle inequality, x plus m1 plus y plus m2 norm, this is less than or equal to norm of this element plus norm of this element. So from here, using these two equations, x plus m1 norm is less than or equal to this, and y plus m2 norm is less than or equal to y plus m norm plus epsilon. So using these conditions here, and we can write m1 plus m2 because these are both are elements of M. So m1 plus m2, that is also an element of M. So we can take it as m star, where m star is also an element of M. So we can write x plus y plus m star norm is less than or equal to x plus m norm plus y plus m norm plus 2 epsilon. Now we are to find the norm of x plus y plus m. By definition, this is the infimum of the set consisting of norms of the elements x plus y plus m. Here this m belongs to m. Now, as we already discussed, this is less than or equal to, because this is infimum, so that will be less than or equal to x plus y plus m star norm. And this is further less than or equal to x plus m norm plus y plus m norm plus 2 epsilon. This epsilon is arbitrary, so we have proved x plus y plus m norm is less than or equal to x plus m norm plus y plus m norm. Now, using this in the equation A, from there we get x plus m plus y plus m norm is less than or equal to x plus m norm plus y plus m norm. This proves all the properties of norm, and this proves that the quotient space x by m, that is a normed linear space. Now, we prove the next part. In the next part, we have to prove that if x is Banach space, then the quotient space is also Banach space. It means we have to prove that the quotient space of Banach space is again a Banach space. So now in this part we are given x is complete, and we have to prove that this quotient space is also complete. In order to prove the quotient space is complete, it is sufficient to prove that every Cauchy sequence in this quotient space has a convergent subsequence in it. So let us start with a Cauchy sequence in X, and so we can find a subsequence of original Cauchy sequence. Suppose that subsequence we have denoted by the sequence consisting of elements xn plus m, such that x1 plus m minus x2 plus m norm is less than 1 by 2, and x2 plus m minus x3 plus m norm is less than 1 by 2 square. And continuing like this, in general we can have xn plus m minus xn plus 1 plus m norm that is less than 1 upon 2 raised to the power n. So in this way we have obtained a subsequence satisfying these inequalities. Now we prove that this sequence that is convergent. Now to prove this is convergent, let us choose a vector y1 in x1 plus m and a vector y2 in x2 plus m, such that the norm of y1 minus y2, that is less than half. Again we choose a vector y3 in x3 plus m, such that the norm of y2 minus y3 is less than 1 by 2 square. And continuing like this, we obtain a sequence yn in x, such that the norm of yn minus yn plus 1, that is less than 1 upon 2 raised to the power n. Now we prove that the sequence yn, that is a Cauchy sequence in x. So in order to prove this is a Cauchy sequence, let us take n is greater than m, and let us consider the norm of ym minus yn. Now adding and subtracting the terms ym plus 1, ym plus 2 and so on, yn minus 1, and using the triangle inequality, this is less than or equal to norm of ym minus ym plus 1 plus norm of ym plus 1 minus ym plus 2 and so on, and the last is norm of yn minus 1 minus yn. Now using the above conditions, this is less than 1 upon 2 raised to the power m, this is less than 1 upon 2 raised to the power m plus 1 and so on. This expression is less than 1 upon 2 raised to the power n minus 1. Now taking 1 upon 2 raised to the power m common from this sum, inside we have infinite GP, and the sum of this GP is obtained by the formula a upon 1 minus r. So this sum is 2. So from here we have obtained the norm of ym minus yn, that is less than 1 upon 2 raised to the power m minus 1. Now as m approaches to infinity, this expression will approach to 0. So we have proved that the sequence yn, that is a Cauchy sequence in x, but x is complete. So by definition every Cauchy sequence in a complete space that converges in the same space. So the sequence yn converges in X. So let us take the limit of this sequence is y, and this y will belong to X. Now we are to prove that the sequence xn plus m converges to y plus m. So in order to prove this, let us consider the norm of the difference of the elements xn plus m and y plus m. Now by definition of addition in the quotient space, this can further be written as xn minus y plus m norm. Now by definition of norm, this is the infimum of the set consisting of norms of the elements xn minus y plus m, with this m belongs to m. Now we can further write this as because we can take xn plus m as y. So this infimum will be less than or equal to the norm of yn minus y. Now because the sequence yn converges to y, so the norm of yn minus y approaches to 0 as n approaches to infinity. So we have proved the sequence xn plus m converges to y plus m in this quotient space. Thus we have proved every Cauchy sequence in this quotient space has a convergent subsequence, and this proves that the quotient space is complete. So this proves the theorem that if a space is Banach space, then its quotient space that is also Banach space.